another graph physics video presentation. Alright, more Richard Feynman. I'm not just picking on Richard Feynman. I'm not trying to do some I gotcha. I'm not trying to whatever. It's just facts. And everything should be understood in a context and it should be accurate. It's just the history isn't accurate. The story isn't true. What people say and the reality just don't have anything to do with each other, really, and it just should be pointed out that this is not very good science, and for more than one reason. But anyway, so I'm going to play some more Richard Feynman, and so I've never really understood this video. I watched it over and over and over again at different parts of it, and you're just saying, what the hell is he talking about, this spinning clock and blah 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 blah. And I got pieces of it, but it's just part of the reason why I didn't understand is because it isn't accurate. It's just wrong. It isn't describing the real pattern, and if you assume it is, then yeah, you're trying to make it make sense, but it can't make sense because it's not really describing what actually is produced. And this is all part of the hype. They say they have the most accurate theory in the universe, and it just couldn't be more precise and more exact, and it's nowhere close. Yes, some of their science is really good, and then they mix that in with a bunch of stuff where they just make bold claims, and there is no science, there is no exactness, there is no precision. And so I'll play some of this and just kind of point out why this is just nonsense. I mean, it's just garbage, and he made the whole lecture was based on this garbage process that has really nothing to do with the actual facts.
And so we have two surfaces at some distance from one another, so. And then the photon can either come down here and reflect right away, or it can come down this way and reflect from back there. Okay? Now,
I mean, this is another fact he couldn't even be precise about, is whether or not light does actually reflect off surfaces, or whether it reflects off the entire substance it moves through, because he basically states both as being facts.
as it turns out, it's about the same percent. If it's just water between air and air, it's about the same 1 in 25 both times. What's the color? If I'm going to do it with monochromatic light, a light of one color, what can you see in colors? What you see on an oil film, on a mud puddle, or in a soap bubble, when you use light of exactly one color, is not colors, but bands, right?
All right, so he says bands, all right? So this is the part where he's getting it right. So the actual pattern created is a pattern of bands, and they're very consistent bands. Completely no photon, all photon. There is no gradually getting lighter and gradually getting darker. The bands don't look anything like that. I've shown them. The interferometer, for example, different objects that produce these bands, they're real bands. They just don't have a peak brightness in the center, and then they get gradually darker to a little thin line of dark, and then back to gradually on again. So none of that. Nothing anything close to a sine wave. Nothing anything close to, gradually on and gradually off. They're bands of light and dark. Just kind of like the slit experiments, the photon experiment. The photon experiment produces blobs, bands of bright and dark. There isn't any, except in the middle, there's very little indication of any gradually on and gradually off. And the reason why there's some indication in the middle is because part of the laser beam is being unaffected, and that has a gradually off in the sense that it fades to black. But the bands themselves are pretty consistent in their strength.
And dark bands. Places where the light is reflected very well, and places where it's not reflected at all, across the bubble. Now, the position of those bands, if you first look at a bubble with red light, you see bands, black and red bands all over. If you look at it with blue light, you also see blue and black bands.
So now he's just talking about the fact that because they are at a different frequency, they're diffracted a different amount, therefore they're all in different places, and then the colors mix and you get different colors.
But the pattern is not the same. They're displaced from where the red ones were. And so when you have both red and blue, you get purple and red and black and purple and so on. Now, if you add to that yellow with its pattern and so forth, you get all these colors from mixing, okay? So we're going to simplify experimentally, as Newton did, and look at these, this reflection. What Newton, most of his experiments, he did this clever way. He had a beautiful curved piece of glass, which was a lens, and a flat piece, and put them next to each other. And then this was only a very slight curvature. And so he had this gap between the two. And when he shone light this way and looked at reflected light, which, depending on where you looked, see, this is a cross-section of the lens, which is more completely like that. There is some reflection in here, which is irrelevant at the moment. There's another glass plate down here.
Right. And it's just a way of creating a bunch of surface size changes. So all he's doing is changing the size of the air surface. How thick is it? So it's one way of doing a thickness experiment, is to have a gradual change, and that'll give you lots of different thicknesses. And all this comes down to, again, is the wavelength matching. So all this is about is phase change. And that's it. So, yeah, a wavelength of difference. So you have 2 points, and then if you're going to combine another frequency, you have to line up those points in the sense that it has to match, or you don't get anything. And that's sort of the argument, is you don't get anything. And then all the math simplifications he's going to do, all the, whatever you want to call it, all the geometry that's going to be based on mathematics, all of it is wrong, because again, it's assuming that you have this very gradual pattern, like it is a sine wave, when it's nothing like a sine wave. It's pretty much a lot like a square wave or a trapezoid wave, but it's not a sine wave.
When he looked in different places, the light came down all over, and he looked in different places. He was looking at cases that corresponded to reflection with one gap or another gap between the sides.
And the gaps would just represent a complete wavelength of difference. So if the light's 500 nanometers, then you can sort of understand, if I have a distance that's an extra distance of 500 nanometers, that the two beams of light will now be in phase. The one off the top surface and the one off the bottom surface will be in phase. So if you wanted to, you could take a bit of light, a portion of the light from one surface, and combine it with a portion from the other surface. So the first one hitting the top surface, you could combine with the third one coming from the bottom surface. The third one could now be the second one coming off this surface. There would be interchangeable now, because they're of the same phase in their frequency. So if you did shoot two guns, you can understand that you could shoot the bullets in such a way where one gun shot the bullet, the next gun shoots a bullet that takes the second spot, and the next gun hits the third spot, and the next one the fourth spot, and it creates a frequency, but you're creating the frequency out of two sources. And basically that's the real function. And as I'm arguing, the reason why all they're missing in their theory to understand why they don't understand and have to resort to a theory that basically says there's a random God is because they haven't really understood that the photon is a composite object, that it's made up of a frequency. The frequency isn't something it has, like I have a label that says this is my frequency. The frequency is what it does. Frequency is the event that takes place. So when the light's reflecting off the top surface, it isn't in a form that can be seen until you add the component from the bottom surface. That's the part that makes the reflection visible. It'd be invisible without the bottom component. Just like all the fringe pattern that's made in the double slit experiment is being made out of remade photons, that is, contributions from both slits. And without the other slit, you get a different contribution. You get 1/4 of the amount of light. Okay, so it's a lot less photons, and it's the contributor of it's adding the second part source, the two new sources that increase the number of photons you can remake out of the first pieces. You're sending a bunch of pieces. Some of them will make a photon, but very few. When you add another source of pieces, now you can make a whole lot more photons. And that's the simple explanation. The simple physical explanation for the cause of the effect. And now I'm going to demonstrate why even his generalization of saying let's forget about causes and just do mathematics, let's just calculate, shut up and calculate, his calculations aren't even accurate. They're not describing the actual pattern. Just like the double slit math doesn't describe the actual pattern. The actual pattern isn't a sine curve. The actual pattern doesn't gradually go on, gradually go off. All of these were obvious facts. Again, I can go all the way back to the Young experiment and point out that it was wrong. The drawing isn't correct. It isn't mathematic. The geometry of two waves doesn't work. It won't explain the double slit pattern. It won't put the little bars of light in the right place, and it won't describe how they look. They won't describe the intensity correctly. And, you know, this is a kind of, I mean, this is just so overtly wrong. I mean, it should have been caught a long time ago. It's just, well, we can't say that because it just isn't true.
When he looked at this with monochromatic light, looked down on it, since it was a circular, a spherical lens, he saw in what I call bands, in a soap bubble, but more organized, he saw rings, called Newton's rings, with a black area starting and then red, if it was red light he was using, and black, red, and so forth.
Right. And again, I've shown these thin film patterns before. It's just so obvious. They are bands. There's just absolutely no evidence that it goes gradually on, gradually off. No evidence whatsoever. No sign of the sine wave. No sign of it whatsoever.
These looked like they were coming closer and closer together, but he was a clever man and understood immediately what it meant. If he measured the distance from here to here and plotted the answer for whether it's red or dark against this distance, not against this, instead of measuring away from the center, he measured how...
He's saying, okay, measure from the other place where there was light and just double it. Well, that's doubling the wavelength. Where there's light, it has to be a wavelength of difference, right? Your first one has to be a wavelength of difference. It has to be that 500 nanometers if your light is 500 nanometers. So that's a wavelength of difference. So 1,000 nanometers, yes, that'll be another place where it'll match. And then 1,500 will be another place where it matches. And then 2,000 will be another place where it matches. And that's all there is to this. It is completely uncomplicated in understanding that what he should be just saying here is that this is just a phase change. You have one full phase change, another full phase change, another full phase change. And that's all the bands are being made out of, is where's your phase change.
Far apart these plates were. Then he found, like our friends the Mayans, every time you had 365 points, they got black. In other words, if this was black and this was red, then double that distance was black again. And, yes, and triple the distance was red. And 4 times the distance was black, and 5 times the distance was red, and so on, nice and even. In other words,
right, as long as you got your first one right, in the sense that you're recognizing that you have to first get that first quantity. I mean, if you double 1,000, well, you're going to miss the 1,500, right? And then you double 2,000, and you're going to miss the 3,000, the 350, you know. You're going to miss all the increments. So you have to get the elemental phase change of 1 first. That's the one you want to start multiplying, the 1.
Instead of measuring by this distance, by measuring the thickness, you find the following experimental result. Reflection coefficient against thickness between the two layers. Okay? The spacing.
Right, and this is wrong. It's just not right. So he's showing you a graph of reality, supposedly, but it's not the reality.
Between, in this case, if there's an oil film bubble, with that's the distance. In this case, it's the spacing between the lens and the plate. And if you change it, it's harder to change in a soap bubble under control, but it changes automatically as it dries out. You get the following. You get no reflection if the thickness is 0, then you get a strong reflection for a certain thickness, and then if you make it thick, you get no reflection, you get no thickness. Reflection, then you get no reflection, you get no reflection.
All right, so again, they're drawing the sine wave. It's not a sine wave. It doesn't go peak to light, then gradually go down to a peak of dark, a little bright dark line, a little straight, hard, dark line. It's a square wave essentially, okay, with a little bit of this, okay? So the wave is this, pyramid cut in half. That's what the wave really looks like. That's what it ends up being as a fact. This isn't accurate.
And so on and now it's getting thicker and thicker. Does this go on forever? Yep. If you got good enough monochromatic light and get the experiment under control, you can make it go almost indefinitely. You can make.
Well, you really can't, just because their light takes in all. There's what you're really doing is also causing the light to slow down. It takes time for it to reflect. It takes time for it to be transmitted through a substance and then reflect back up. So you have to add that into the whole thing, and
make this work for distances of a meter or more. Still keeping track whether it's even, odd, bump, bump, bump. Okay? There's nothing. That's interesting, very interesting, but that's damning. Why? Because what theory were you figuring for the reflection from that? That made the reflection be 4%. The odds, 4%, whatever. You put another layer down here at the right thickness, expecting to get 8%, and you get nothing. How does a layer down here turn off the reflection from the layer up here?
Okay, so the simple answer is it doesn't really turn it off. It just makes it 4 times brighter, so it can amplify the parts you're throwing off the top surface, but that's all it can do, is take the parts that are coming off the top surface and make more of them into photons. So it can fix what's already broken. And it does it in a way that looks like it's making a 100% contribution, but it really isn't. The fact is, it isn't a 100% contribution. It's just 4 times brighter. 4 times more potential to make light, to make a photon, when you have the bottom contribution in phase. So when the bottom contribution's out of phase, there's some point where it just breaks off. So if it's, I don't know if I need to draw this part. You can understand the middle is here. Okay, so I have a wavelength, and I have some point I can be where all of a sudden now I'm going to be too much out of phase. This one and this one aren't going to match by a certain amount. Now this is a 0. This would be your 0, right? Because they're out of phase completely. All right, they're not even close to being in alignment with each other. This would be the way to show alignment, I suppose, or maybe even this, where you have equal distances, and you're making the equal distances out of 2 contributions, right? And this is you're completely out of phase. And the truth is that the dark bands won't be anywhere near the same size, and so it's going to be more like, okay, this is a photon. Even though it's out of phase, it's a photon. It works. It'll function. So they can be a little bit out of alignment and still make a photon. But they get to a certain point and then it just cuts off, and now the phase is too broken. So it's like it has a little flexibility, and that's why the light bands are wide and the dark bands are narrow. Now in thin film, they're a lot more consistent. So it's clear that in thin film, it might be a more precise way of reconstructing photons, because the light and the dark bands are a lot more even.
Or, if you figure that out, and you make the layer just a little thicker, it doesn't turn it off, but in fact the reflection is more than twice.
See, in this lecture, he could have just pointed out phase. He could have just pointed out, it's not that complicated a subject, just to say, if you can get back to a layer that's got, where you have a whole phase difference in length, then you're back on again. But the phase difference won't be the exact measurement of distance, because again, you have to account for the reflective index, or the the fact that the force, whatever you want to call it, the light, is traveling slower as it moves through the medium. So the distance won't be the same distance, because it's going to be augmented by how much time delay there is in the light moving through the medium. So 200 nanometers could create 500 nanometers of difference in the phase, in the speed, in the time it shows up.
This scale here, this line would have been what you would have expected if you expected it always to be 4% plus 4% or 8% from the two surfaces. This is what you would have got if you disregarded all this nonsense that actually...
So it's you keep switching between 2% reflective index and a 4% reflective index, which is sort of understandable because you keep switching between water and glass. But yeah, it's,
You have it. By common sense. It reflects with a certain odds and it reflects from the other surface with a certain odds, and so altogether you get twice as many coming back. This is the twice as many. But for some, if the thickness is 0, you don't get anything. If the thickness, hey, that's not such a bad idea, is it? If you don't have any water there at all, you wouldn't get any reflection. Starts out right anyway. So that theory...
See, but the truth is that that's where you're starting to go out of phase. So you start at being in phase, and now every movement forward is getting more out of phase.
It's kind of dumb now that I come to think of it. And that helps to explain Newton's observation when the distance is too small, the light doesn't know anything about it. If the thickness...
Right, well the thickness can't be 0, so that's the whole point. So any finite beginning that you have to have a certain number of atoms. And once you've added 4 atoms or 5 atoms or 6 atoms, maybe you've got enough now to cause enough of a phase difference where it's already off, and now you're going to have to build up until you get to 1,000 atoms, and then you'll have a whole wavelength of difference again.
Sufficiently small, it doesn't reflect. It does exactly the same as if there's nothing there. But the horror of it is, it's all right that it increases as the thickness goes up, but it all...
So again, it doesn't increase, doesn't do it in this progressive way. It does it rather dramatically. In a very short period of space, it will be on, and then it'll stay a consistent amount of on, and then it'll go off again. So this is just wrong. It's not accurate.
It overshoots, you see, and then it comes back to 0 again when the thickness is just right. It's very difficult.
So I mean, they gave them the Nobel Prize for this kind of math, and it's just kind of surprising that it's this wrong.
To invent a probability thing. If I had these spots on this surface, it's very hard to see how you're going to have spots on this surface, which turns the spots on that surface off when they're the right distance away. And so Newton went a little bit nutty. And he talked about fits of reflection and transmission and so forth. And I would like to now just finish this by telling you...
Right, and so it's just, it really is a real thing, okay? They do this particle wave thing, and they just don't recognize that the frequency is the real thing. And that frequency implies, kind of clearly, that a photon is delivering a frequency. And to deliver a frequency, something that's happening with a period of time stuck in it, that this whole thing called a photon would have to happen over a period of time. You can't have frequency without time. So it would have to be, a photon would have to be a train with cars. It would have to be some kind of thing that has some recognition that it's a timed event. And it's only when 3 cars go by or 4 cars go by, that's a photon. So the element of the photon can be a particle, but the photon itself has to be a timed event of the particles. And if they had just thought of that as one of the possibilities, then they could have understood that, oh, I can rearrange the cars of the train. I can take cars from over here and over here and over here and over here, and as long as they're the right distance apart, I can recreate a train, or what's seen as a photon.
What is the answer? Now here's the answer. This is the way we figure this out. It goes as follows.
So they didn't figure anything out. He just tried to make a simplification of it, and he simplified a generalization that was wrong. So it's a simplification of a wrong generalization. So the wrong generalization was, well, we'll just accept some sort of, the Young two-wave thing. We'll accept that the pattern, even though it doesn't look like it's gradually on, gradually off, gradually on, gradually off, we'll just accept that it is. And now we'll do a simplification that will create the same thing in terms of understanding that there's a cycle, so we'll make it a circle, and it's kind of like just a piston on an engine, right? I mean, the camshaft, the crankshaft moves round, okay, and the piston moves up and down, and all you're really saying is okay, when the piston's all the way out, the round part has to be here. When the round thing has to be over there, and so you're turning something round into something digital, binary. You're changing an analog system into a digital system.
What we're going to calculate is a probability. The probability of a particular question. And then the probability that this counter goes off. The probability that if I had one photon coming down, it'll come back to this counter.
So it's not really a probability at all, because he already knows, a probability in terms of some randomness, because we know all we do is change the distance between the two surfaces, and I change that probability. So we already know this isn't like some ambiguous, unknown cause of an effect. It isn't just random, it's clearly dependent on where that surface is, and where that surface is clearly going to define whether you're in phase or out of phase. So there's absolutely nothing in this that has anything to do with some sort of uncertainty. There's a clear certainty between where that bottom surface is and what the probability is that you've remade photons. So the whole way he's describing this is just poor.
The probability, which is measured by this curve. And here's the way that the rule.
So it isn't measured by that curve. That curve is incorrect.
Is for finding the probability. Now listen, hold your seats now, hold on. Don't be afraid, just go on, all right? Never mind if you don't like it, huh? Just hold on.
See, it's amazing he has to say all that, right? And still none of the critics could put together a coherent argument to point out that you really can't do this. It's wrong, it's not accurate. And you're really completely obscuring the vision of the real thing that's important, which is the frequency. You're just making that irrelevant, and that's the most important thing the photon has.
It works like this. What you do is you take a piece of paper. A piece of paper has nothing to do with the original thing. The piece of paper is only to make marks on. It's got nothing to do with the light. Now, have your following rules. That you make an arrow to represent, well, for each reflection, you make an arrow. This arrow, for example, is for the reflection from the front surface, and this arrow might be the reflection from the back surface. And I'll tell you in a minute how to make those arrows. And then what you do is you tie the arrows together this way. You make one and then the other. All right?
So all this represents, see, this fooled me because I just didn't get it. All this represents is the arrow is telling you that's the phase. Okay, and the complete opposite phase is the opposite arrow. So it's telling you that this, if I go this far around, okay, that much time to a point, that will be the halfway point of the phase. So that would be completely out of phase. So if one arrow is going this way and the other arrow is going that way, that just means that's the second arrow is out of phase. I've now made this the surface of the glass where it's 250 nanometers of 500 nanometer light, and now we have 250 nanometers of change in the glass, and now it's a full half wavelength out of phase, and therefore there's not going to be any photon. And then if I wait and go around another 250 nanometers, and that's all the circle's doing, is saying a complete circle is 500 nanometers, a full wavelength. That's all the circle is doing. Alright, so it's just telling you what a full wavelength is from wherever you draw your first arrow. Whatever position you put it in, you're just saying how many nanometers am I going from that first arrow. And if I go a full circle, that's 500. That's all that it is. So if I have two arrows pointing in the same direction, there's a high probability, right? You get a very long line. There's a very high probability that you'll get light. And if I have the two arrows going in the opposite direction, then the two cancel out, and I have very low probability of getting any light because I'm now at the half wavelength point. And that's all this is. So this seems more complicated than the simple explanation that you're just saying, as you move the surface, how in and out of phase am I? And the real point is that all of this geometry, okay, where he's taking arrows and saying, okay, this first arrow is this position, and now I'm just going to calculate how how many wavelengths I'm off. Okay, and so I can just do that with any kind of, doesn't really matter how many there are, it just matters whether you're in phase or out of phase, whether you're a multiple of the first arrow, a multiple of the 500. So if you're not an even multiple of the 500 circle, and you're some other thing, then you have two arrows that are doing two different things. And then he's saying that all I do is draw a line between those two, make that circle, and that's the probability. That's what's not true. That's true for a sine wave. It's not true for the actual experiment. So again, all of these drawings are useless because they're really not going to describe the actual experiment. They're not describing how the actual bands, as he called them, bands of light, the actual bands of light will not duplicate what he's saying they are. So he goes to all this trouble to do all this probability math, and the probabilities aren't even accurate. So I mean, this is a dramatic fail in terms of doing good science. He doesn't have an equation that actually predicts the real results. He's predicting fake results. He's predicting what a notion of the pattern, some vague idea of what the pattern looks like, but it's not the actual pattern. And this is glaringly wrong. It's not like a little bit wrong. No, it's completely inaccurate. I shouldn't be the only one saying it.
That means you make this arrow and then you put the tail of the other one on the head of that one. There's the first arrow is a reflecting arrow from the first surface. And this
all that angle is telling you is how much out of phase they are. So if it's 180 degrees, they're 180 degrees. They're 90 degrees out of phase. They're completely out of phase. The more you bend it, the more you're putting them back in phase. And if you can get them to point in the same direction, then you're completely in phase again. But the line between them will not create anything real, because there won't be, the line predicts a very gradual increase in the brightness. It goes from zero brightness to a little tiny bit, a little higher, a little higher, a little higher, a little higher, a little higher. None of that happens in the reality. The bands are clearly on and completely off. Completely on, completely off. Not even completely. Again. Okay. But they're all consistent. Consistently low amount of light, high amount of light. Low amount of light, high amount of light. Real binary. A square pattern. Not a sine wave pattern.
The second arrow is the reflecting arrow for the second surface. And you put these two arrows together by this rule, and then look at how far off you've come to the end. Yes? Yes? To count the pins in the hole, to count the number of beans you put in the barrel. I mean, you make these pictures. And then you ask, how big is the circle? In area. That area represents the probability that you get the thing back. If the circle area is big, then you get a high probability. If the circle area is small, you get a small probability. And I just have to say one more thing of how to make the arrows.
So theoretically, if you put the arrows on top, see if he did it and said, well, look, this is a full, when they're back in phase, a full wavelength, I just put another arrow right on top of this arrow, and you could sort of understand if that was a real triangle, I could make a hypotenuse out of that line. I could make a hypotenuse out of that line. I could say this is side, and the second arrow would be a side, and I could make a hypotenuse out of that one straight line, I mean, you could say they're a little tiny bit off, and then I could draw my straight line hypotenuse and say there's a 100% area. The area will match what 100%, the biggest circle I could draw. The biggest circle you can draw out of the lines is defining the 100% probability. And so all you're saying is by deviating the lines, I make that circle smaller and smaller and smaller. And again, it would be gradual. And there's no evidence that the pattern is gradual.
Answer. Well, the size of the arrow depends upon the particular materials. I won't come into that right now. The absolute size, 4%, is another matter. What you do is you make an arrow, and depending upon the time it takes for the light to get from the source where it started to the place where you want to count it, you turn that arrow like a clock, depending on how much time. So if it takes a long time, so you start out at the source, there's the arrow for the source, but that's not the arrow you want to draw. This is just a thinking arrow. And then you say, turn over, ding, 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 round, 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 depending on how much time.
clock is turning the wrong way, which doesn't make much sense, but whatever. Feynman wasn't too good at figuring out that time is, a forward-going thing. You can't steal energy from the past and use it in the future. I mean, you can't steal it from the future and use it in the past.
At a certain rate, every second it goes around 75,000, goes around a hell of a lot of times. It goes around 1 followed by 15 zeros. Time in 1 second. It doesn't take light very long to get to from the source. But it still turns around a lot of times.
So let's understand. It's going to travel faster through air, and then it's going to be slowed down. It doesn't go slower. It is slowed down by the transmission process. So it's obviously distance is going to be doubled inside the surface in a sense. If it's 40% slowed down, then you can figure that, well, it's generally speaking double. But yeah, there's something more precise. So how much the true distance of the glass, the thickness of the layers, has to be understood that thickness is going to be, the time is going to be affected. Distance and time will be different than they are in air. In air, a wavelength is 500 nanometers. In the glass, it's going to be 250 nanometers, or 750. Yeah, well, it's slowed down, so it's got to be 250.
You turn it around, okay? It's like the
300, whatever.
roulette wheel, and then just at the moment it hits the counter, it happens to be sitting at some angle. All right? And that's for the reflecting from the first surface. Now, what about, that was supposed to be this one. I've gotten too many arrows on here. What happened is you take the first surface reflection, turn it toward this angle depending upon the time, and it ends up here. Say, that's not a very big angle. You said
it doesn't even matter where it ends up. Because all that's going to matter is whether the second arrow is in phase with it or not. So you can draw it in any orientation, and you're just going to start with that orientation with the second arrow. The amount of added distance is just going to be added to wherever the first arrow stopped, obviously. Obviously, its position is going to be dictated by the first surface. So now you're just adding to that position for the second contribution.
Big angle. It is a big angle. If you keep on turning, it can look like a small angle when you're done, but you had to turn around and around and around and around, right? You know what I mean?
Yes, so all the turning around is completely irrelevant, because all you're saying is the distance a whole multiple of the wavelength? That's the only question you're answering. You don't care. I don't care how many times the clock spun around. I don't care how many wavelengths of distance I have. The only thing that's going to matter is this surface, okay, a whole number of wavelengths different than this surface? Is that line represent, when I divide the wavelength into it, do I get a whole number as the answer? A multiple of. Got to be careful, just because depending on how you do the math, the half multiples are to the odd numbers, and the even numbers would be the whole wavelength.
It goes around like a clock hand. After 25 years, it's still saying it can start at 2 and end up at 2:15. Yes, 25 years.
Right, and all that matters is it has to. If you want to be in phase, you have to stop at the same location you started at. And that's all. That's all this is saying.
Yes, it went around. So here it is, having been turned around a lot of times. Okay, this is from the first surface, I should say. That's the arrow for the first surface. Now the arrow for the second surface, rule. Same as the arrow for the first surface, but in the other direction. It's just an accident. It happens to be the opposite direction.
They have to start it in the opposite direction. That's because of the difference in the, the surface material. So it's not really a phase shift built in. The phase shift is going to be based on the time shift, the fact that distance isn't going to mean the same thing.
It starts because, well, not because, the rule will turn out later. When you go from air to glass, it's one way. From going glass to air, you change it around. Anyway, you start this way with the second surface, and you turn this one. No, which way did I turn? Yes. For the time. And when you get finished with this roulette wheel and the second one, it comes out so. And then you add them together the way I said.
Yeah, and now all you do is figure out whether they're completely out of phase, pointing in opposite directions, or almost in phase, pointing in the same direction, and that's all. And again, even if you do all this crap, you're getting the wrong answer, because there isn't any gradual on and gradual off. That's not what the actual experiment demonstrates. So again, all of this to get the wrong answer. To have a method of calculating that doesn't calculate the correct answer. I mean, yeah, well, what can I say? I just, it's hard to believe that all the physicists just fell for this crap, and that nobody ever said, you know what, I got to challenge that Feynman stuff, because frankly the pattern doesn't look like that calculation at all. If I wrote those calculations down and then I went to the actual pattern and measured it, it's not going to come out right. This way of calculating doesn't work.
You tie one on the other end and make the circle. And that's the laws of light. And that'll tell you whether it reflects or it doesn't reflect. And what difference does it make? Why do I get these ups and downs? Well, sure, if you move this, kept that the same and move that, what is that going to do to my exercise over here? Answer. The first arrow, the time doesn't depend upon where the other surface is, so it does exactly as I did before. I'm doing the same experiment with the bottom surface a little further along, okay? Top's the same place. Now the second one, however, when I went to turn it, it's a little bit further. It takes a little longer to get there, and therefore it's turned to a new position. So this second time, the picture would look, if the thing was thicker, the picture might look like this. Instead of being here, since it had to turn further, perhaps it's turned to here the second time. And then when I add these two things together and tie one on the end of the other, and I just do that again here, you see that this line is now a long line, whereas before it was a relatively short line. This, remember, was the answer line. The answer line is a longer line, and the area here is much bigger of this circle, and the probability is larger.
Right, so anytime the line is on that one half of the circle, you're going to be adding, making the line longer, the probability higher, and anytime it's going in the opposite direction, it's going to be less probability. But again, the probability is not it's not accurate. Again, that's all you can, what can I say? It's not going to give you the right answer.
And this upping and downing, and the answer, this comes out exactly predicted.
See, it doesn't, and so that's all part of the quantum mechanics hype. We have the most proven math, the most established, the most perfect, the most blah blah blah, and they can't even do two surfaces of glass correctly. So I've already pointed out they can't get the math right for two slits. They can't get the math right for two surfaces of glass. And how can you trust any of what they're talking about? How can you trust them when they talk about taus and muons and all this other particle zoo crap, all of this stuff, when they can't describe simple experiments and actually do it consistent with the actual experimental results? Their math doesn't work.
Well, just by this little game. All right? Now, that's a shock, huh? You say, yeah, he's going to explain why it's like that. That's exactly what I'm not going to explain. I don't understand it.
So he's saying he doesn't understand it. I don't know whether that's a joke or not. I mean, I think he does understand that it's just about phase. Okay, that all you're doing is saying, when have I changed it? When have I put the things back in phase and they're out of phase? In phase, out of phase, in phase, out of phase. I'm sure he understands that. You could at least tell the audience that. And I'm just talking about phase here. That's all these arrows indicate, is whether it's in phase or out of phase. That's it. Close enough to make a photon, not close enough, no photon.
That's the way it works. What I'm going to do in the next lectures is to tell you sort of the generalization of this. This is a special example for reflection. I'm going to tell you how the rules go about turning arrows.
So he really isn't going to do any of that in any, in any specific way, getting to any specifics, because that's what they concede. They have to know everything about a system for any of this to even work, this probability math. You already have to know every variable to be able to do any predicting with it. So they say they have the most predictive math in the history of mankind. No, it doesn't predict anything unless you know every single variable, every little bounce of the die. They don't have an equation for the dice table. They don't even have an equation for the roulette table. Theoretically, in the sense that they they can't know all the variables. So the roulette wheel could have a little fluctuation in it, a little tiny difference in distances, and they wouldn't be able to calculate that. They wouldn't predict it. All they can predict is some standard outcome based on how many theoretical numbers you could put on a round wheel. It's a prediction a 10-year-old could do.
In fact, somewhat simpler than this example. It's not bad at all. It's easy. It's not hard, but much more generally. And what I've done is this is a prototype of the general.
So I'm just saying that. So he's talking like, well, I'm going to use this great working theory to generalize about a bunch of other stuff. So it doesn't work in this specific case, and he's going to say, well, let's apply it to a lot of other things like basketballs and hoops and different things. Let's apply it to everything else in the universe, even though I haven't even established that it works at all, that it's even close to the right answer.
Result. There is no secret behind it that we can do any better than give you that result. All I'm going to do is generalize it. It's going to sound something like this. This part you needn't understand right away. It's what I'm going to elucidate in the next lecture. The idea goes as follows, in general. It's just a statement, and I'll come back and do it again, so don't worry. To calculate the probability of an event, which can happen in a number of different ways, the probability of an event is always what we call the square of an amplitude. Or in this model, it means the size of a circle corresponding to an arrow. An arrow is called an amplitude. For every event, you calculate an amplitude, which is an arrow on a plane.
Right. So again, this is only for events that are frequency dependent. So again, this won't work if some other variable besides phase and in phase and out of phase is going to decide your outcome. This isn't going to help you very much, or at all. You have to have some kind of cyclical event. So only things that are cyclical is this going to work. And again, it's only going to work if it's cyclical in some sort of sine wave manner rather than cyclical in some sort of on and off way. If it's an on and off way, it's not going to tell you what that on and off trigger is. It's not going to tell you how much out of phase the bits of the photon can be and still be recognized as a photon. This will not tell you the answer.
The probability is the area corresponding to that arrow. Right? That's the first thing. Second, how do we calculate the amplitude for an event? If the event is simply a photon going from one point to another of a definite color, then it's simply an arrow which turns depending on the time. And that's the amplitude. Notice, by the way, there's no reflections.
Yes, notice, by the way, again, that it's the wrong pattern. Okay, he's not predicting the actual pattern. Just say it again and again and again.
There's no trouble. It just turns. The area stays the same. The probability of finding a photon is not altered. And even though the arrow alters, its area is the same. That's when we get in trouble. When we have more than one way to occur, then the rule goes as follows. If the thing can happen in more than one way, then you find the amplitude. What that was, the arrow, for each way. See, if it could happen in two ways, you get the arrow.
Right, so the roulette wheel could happen in 32 ways, or whatever the number is. And so you just make 32 arrows.
Arrow one way, and the arrow the other way. And if it could happen three ways, if it was a double layer of stuff and so on, then you put another arrow for the third way. Maybe that was a short one. And if there's a fourth way, you put another arrow. And when you're all finished, you put them tail to tail, all the possibilities, and find the total.
Right, and all that would only matter if the event is triggered by some frequency-dependent regularity. There has to be some regularity in the system that is frequency-dependent for any of this arrow crap to matter.
Total, what we call the total, or the net result of making all these little arrow steps. And that final arrow is a total amplitude, we say, for the event to occur. The probability is, as always, the area corresponding to that arrow. Now, that's kind of stinky, right? Well, it's fun, and it's strange that nature's like that.
Okay, nature isn't like that, and I don't think it's fun. So I disagree entirely with that. It's just my personal opinion. Didn't think it was fun, and that's not the way nature is.
I hope you come back to hear how it works in general, a little bit better statement of this to review it. And one other thing, I am going to try to explain to you how this rule explains several of the ordinary phenomena that you're used to in light, such as angle of incidence equals angle of reflection, and reflection, that light bends as it goes from air to water. And
it won't explain any of it, so again, you can sort of figure that out ahead of time probably. There won't be any explanation for why it happens. So it really won't explain any of that.
It travels in straight lines from point to point and so on. It's all hidden in that one rule. And how that one rule carries all this information is part of the next lecture, as well as I would tell you right away one more thing. that this rule, that to figure out what happens in nature, you have to calculate an amplitude, is not just for light. It doesn't make any difference what happens. An electron does something. A nucleus explodes. Doesn't make any difference. How do you find it? You can only calculate the probability it's going to happen. And how do you...
Right. So, again, that's just giving up on cause and effect and assuming that everything is phase dependent, which it isn't. And he even admits in this video that they don't have this trick for figuring out where protons are going because it doesn't work. Yeah.
Do that, you can guess. You calculate an amplitude, that's a lousy little arrow. And the probability is the square of the amplitude, we call it. That's really, we should call it in our case, the circle of the amplitude. The circle that represents the amplitude.
Phase. It's either in phase or out of phase. 12 o'clock, 6 o'clock, 3 o'clock, 9 o'clock. There's either in phase, out of phase.
Probability. And that's true not just of light, but of the whole structure of nature as far as we can tell. And although quantum electrodynamics is only about electrons and light, we discovered that part of the rule, at least, is valid also for nuclei, nuclear particles, quarks, and everything else.
Right, so he just did all that. It isn't valid for these simple experiments that he's misdescribed, and it's certainly, I would argue, probably not valid for anything else. He hasn't even, the demonstration, they have a demonstration model, and it doesn't work. Okay, so the rest, the ones in the plant don't work either, so don't go to the store and buy it. Because it doesn't work.
The thing that is special about electrodynamics is our complete knowledge of exactly what the rules are for drawing the arrows. But the fact that you have to draw arrows and end up calculating probabilities like that, which is such a shocking and horrible form for nature, is something that I will talk about next time in further detail.
Yeah, you won't do that either. There's no detail. I mean, there's your further detail is we don't know what's really causing it, and so we just made up this crap that it's somehow, the universe is wacky. And it's a silly explanation. It's not even close to a good guess. It's a shitty guess.
Thank you very much.
These rotating arrows are all very well, but is there another model?
Right. Is there one that actually gets the right answer? Yeah, so you could add that part. One where you actually get the right answer. Because what you said here or implied here isn't actually true. It's not what the pattern actually looks like.
The question is there another model? Naturally, we struggle to find it. I'll tell you.
Yes, naturally. We are smart and we haven't figured it out, and so we had to give up and pretend the universe is made out of probability math. And even though our probability math doesn't even predict the right pattern.
The answer is what's going to be in the fourth lecture. Nobody can find one. It's worse. We're not so dumb. We're pretty advanced compared to them.
No, you're pretty bad because, like I said, it isn't that hard to look at the pattern and say, you know what, that's not a sine wave pattern. That's not getting gradually lighter and gradually darker. It's clearly bands of light. So I guess this whole thing I'm saying can't possibly be the cause or the right answer because it's not the right pattern.
We've analyzed it very carefully. We almost prove it's impossible to find one over a wide class of ordinary possibilities.
Right. See, this thing is so simple. Yeah, it's so simple that, again, you didn't figure out the most important feature that a photon has. You're sitting here making diagrams showing, convoluting phase into some circular thing and all of that crap. And if you just recognize that a frequency means that it has to take time, it takes time for the photon to do its thing. It isn't an instantaneous event. There isn't just photon hits, photon is made. No, its photon is a sequence of events that happen and over a period of time. Once you recognize that, then it's easy to see that, yeah, a photon can be made out of pieces.
It's going to be any kind of a model. It's going to be at least as weird as this thing.
Yeah, sorry. No, it's pretty simple. 2 + 2 + 2 physics. All done.
The reason is that the answers from this are so simple. That is, looks a little complicated, we're not used to it. But mathematically, those forms and those curves are mathematically so simple, and the rules are so simple, it's hard to make any mechanism at all that can reproduce such simplicity.
Right. No, it's really easy. Like I said, photons are composite objects. It's just a mistake to have called it a photon, implying that it's tonish.
The Mayan thing was really fairly complicated. The numbers were peculiar. There's no explanation of them. This analogy, our numbers are not peculiar. Those, they have an explanation for. It's a different situation. One more thing about gravity, I would just remind you, that we don't really have a good model because when it comes to why is it that there's a force inversely as the square of the distance? And what do you mean inversely as the square of the distance? That's mathematical.
It really isn't. It's just geometrical, okay? So you're just saying you go further out, you're spreading the same paint on a bigger wall. I mean, any idiot can figure that out, right? If the wall is this big when it's close to me, and it gets, bigger and bigger and bigger as I go further away, that is, I expand how much surface now covers the angle I can see. If I'm really close to the wall, I just have to do 2 inches of wall, right? But if I move away from the wall gets bigger and bigger and bigger, and I have to spread the same amount of paint on that bigger and bigger surface. They're all done. That's not complicated.
Newton was the one who taught us that we can make progress if you stop arguing about that.
Oh, that's wrong, okay? I mean, Newton conceded he didn't know the answer to gravity, but he wasn't at all disinterested in the subject. He wanted to know the cause. He wanted to know what's the mechanism. He didn't have any give up in him at all, so that's just a kind of a lie. I mean, people asked him what's causing gravity, and he honestly answered the question, I can't posit. It's not even just that he won't posit, it's that he couldn't posit an answer. He didn't have one. Okay, but he wanted one.
He said, I make no hypotheses. I don't explain the gravity law. I tell you what the law is. That tells you how the things look, and you can predict where the stars are going to be. And that's the...
Right, and he didn't, and again, it was not his philosophy that that's good enough. He was perfectly dissatisfied with that as being we're all done with that subject. There's no evidence that Newton was done with the subject.
Pattern, but I don't, at the moment, know. But he left open the question, just like you asked. Maybe tomorrow somebody will figure it out. On your particular question, it's always possible that tomorrow somebody will figure it out, but it's going to be very difficult and very strange.
Yeah, it says him, right? Because Richard Feynman's saying, I can't figure it out, so you losers can't do it because it's just too complicated, too weird, too strange, because I didn't figure it out. Ugh.
Do you like the idea that our picture of the world has to be based on a calculation which involves probability?
See, they should ask, though, again, I should go back to the question, just to point out, that's not the question. The right question is there any evidence that probability is the byproduct of non-existent causes? That somehow probability is being created by some probability, a randomism, or some sort of, make bizarre, weird things happen engine? That there's some kind of mechanism that isn't a causer, but somehow causes random events, probabilities to change? I mean, that's the more important question.
Not really. If I get right down to it, I don't say I like it, and I don't say I don't like it. I am very highly trained over the years to be a scientist, and there's a certain way I have to look at things. When I give a talk...
Right. You have to cheat all over the place to make your bad notions of reality fit the evidence. So you just pretend the evidence is that it's a sine wave. You pretend that it's gradually on and gradually off. You pretend that your bands of light aren't really bands of light, that there's somehow this thing that gradually turns on and gradually turns off, when it doesn't.
Simplify it a little bit, cheat a little bit, to make it sound like I don't like it. What I mean is it's peculiar. But I never think this is what I like, this is what I don't like. I think this is what it is, and this is what it isn't, okay?
So there's no point in doing that when you're wrong. So again, he's obviously not doing that, because he's not paying any attention to what is. So he clearly does think that there's he's setting up as facts a bunch of fake or axioms or notions that just aren't accurate. And he's trying to prove those, rather than look at the evidence and say, what does the evidence say? Well, it says this doesn't work. It should be saying overtly to him, it doesn't work. Just as the Young experiment 200 years ago doesn't work, okay? The drawing doesn't match the pattern. It's a wrong analysis. It's incorrect. 2 waves won't make the right pattern.
And whether I like it or I don't like it, is really irrelevant. And believe it or not, I have extracted it out of my mind. I do not even ask myself whether I like it or I don't like it, because it's a complete irrelevancy. It's a kind of a dumb answer, but it's true. And when I'm
Yeah, it's just a coarse shit, bullshit. I mean, there's lots of things that people have to say that doesn't fit. All right, the fact that quantum mechanics and gravity are completely incompatible. They have stuff moving the same speed. We have forces in both mechanisms, and we have mechanisms in both theories that are moving the same speed and yet are fundamentally and physically completely different. I mean, it's just really doesn't. It isn't very satisfactory as an answer that the universe creates things, like the duck-billed platypus or something. There's something disquieting about the notion that somehow those two animals are somehow related. Okay. And there's something disquieting about saying, well, it's just a coincidence, because there's more to it than that. And so then you have to start doing some analysis about the advantages of having, hard lips.
I shouldn't have said I don't like it. What I was trying to say is you probably don't like it. There's nothing I think we can do about it. It might have been something else. I don't know how else to express it. It's not really personally a dislike.
Have you left out anything in this lecture which you need to add later?
It's very difficult, and I worked very hard on the lecture to try to use...
See, sorry about the audio is just not great on this videos, unfortunately.
Just my examples, things that I didn't have to change later, the interpretation slightly. I couldn't get an elementary enough process that I didn't have. Later on, I have to make a little change. You see, we talk and we see as though it's reflected at the surface. Actually, what's really happening, and a deeper understanding, which I should do later on in the lecture, but I might forget, is that it's reflected by cause. It affects electrons in here, which re-emit light here, or here, or here, or here, or here, or here. And what really is the things that we have to...
Yeah, so the things you really have to add up are a bunch of little pieces of photon, not one piece, and not a whole photon. The photons are being generated by events, okay, that are discreter than the photon. The photon is made of a combination of events, not just one event. But it's still a surface phenomenon. So here he's both stating both. He's saying it's a surface thing in one statement, and then he's saying, okay, it's happening as a bunch of little arrows. No, it really isn't.
It is not the arrow from here and the arrow from here, but a whole lot of little ones from all the distances from there to there. But believe it or not, you get the same answer. Okay? So what I really ought to do, and I would do if I were doing it correctly, would be to talk about the reflections from every interior part and adding arrows. But I would rather add just 2 arrows the first time than an infinity of them. So I didn't cheat a little bit, but I got myself in a slight hole, which you picked up.
So you could argue that when the light's coming in, it's bombarding it, right? Because we can't send just one photon. So there's a bunch of light hitting constantly. And each piece in each one of those photons has a different phase number. It's starting with the phase. One that hits this millisecond, then one that hits this millisecond, the one that hits this millisecond. They all have a different phase. So obviously at different distances, each one will be in phase with a different one at a different distance. So you really just have to understand that light is hitting the surface so much light and at such a constant rate. That's why you could argue that the reflections could happen from any location. But that argument can sort of be defeated by laser light, I guess, if you start measuring with laser light, because then all the photons are coming in clumps, so to speak. They're all in the same frequency, and they have some consistency in their timing, and so they're all in phase. And then you can sort of eliminate this argument that it's being reflected from all the locations.
The actual reflection is from the material. The electrons in the material.
See, I would argue that it's not even the electrons. Frankly, it's protons. Okay, so the reflected bits are the pieces of the photon that didn't hit an electron. They actually hit a proton and got diverted, but whatever.
In the case of Newton's thing, it's because the electrons which are reflecting from the glass here and here are interrupted in their pattern. And when you add the arrows, it comes out to be, believe it or not, the same as if you just take the one from here and one from there. Perhaps just for those who can, I don't want to make it too hard, but just to give you a clue of the marvelous way it works. If you added tiny arrows to represent reflections from everywhere, instead of just talking about it reflected from here to here, which is a good equivalent way, But if you took a whole lot of little baby arrows, each one a very, very tiny angle from the other.
So you're just saying a tiny change with distance. So tiny distance difference is a tiny portion of the phase. So this would be 5 nanometers plus 5 nanometers plus 5 nanometers plus 5 nanometers. And you go all the way around to a circle and you'll do the same thing.
All the same length, which is the reflections from all these places. You see, you generate a circle. And what I was using instead of the circle were the 2 arrows, which were the beginning arrow and the end arrow of the circle. And what you told me is I shouldn't talk about the reflection from the front surface and the reflection from the back surface. I should talk about the reflection of all the stuff in between. But it's equivalent. The net result of going around here is the same as going up here and back on that one. It even accounts for the minus sign of it. That is, the distance from here to here is what you get by putting onto this arrow this one backwards. Well, I got the distance is the same, see? So I got it upside down in my book. But this line is the same line as you would get by going in a circle. So it's really reflective.
Well, whatever. The argument is still that's open for discussion. Okay. Whether light actually is surface dependent, and I'd argue that I think the evidence kind of indicates that it is the surfaces. Surfaces are different than the inside of the material, and that's why surfaces do something different to the thing going through the surface. That's why it's diffracted. It's diffracted at the surface. It isn't diffracted all the way through, because then you end up with a curved line inside the material. Obviously, the diffraction is happening at the surface.
In the interior. But in the first lecture, I thought I'd just get 2 arrows instead of an infinite number.
Does your picture apply to anything besides electrons and light?
This aspect is universal over the whole of the world's phenomena, as far as we can tell. Not just.
All right. So again, everything's a sine wave. That's all you can say. That's what that's essentially saying. Saying everything's a sine wave. No, it's not true. I'm not a sine wave. Volkswagens aren't sine waves. Electrons aren't sine waves. It's bullshit.
Just light and electricity. This phenomenon of drawing arrows and making areas for probabilities. Probability amplitudes, we call them. The amplitude and the probabilities are the squares of these amplitudes or the circles of them. That's universal. The next problem is a rule for how to draw arrows under different circumstances. What kind of arrows do you draw under different circumstances? What are the rules? One of the rules I told you is it turns at a certain rate for light and so on. Those are the rules that we do not know well in the case of the nuclear phenomena. But we know virtually exactly, or at least as far as we can tell experimentally. I lost my numbers.
So as far as we can tell experimentally, again, it's just all inaccurate. It's based on a wrong premise that this has something to do with some sort of innate frequency that isn't made out of elements. That somehow you have a frequency without elements making the frequency.
For electrons and light, the rule for how to make the arrows is apparently completely known. Nothing is ever.
Well, see, it's apparently completely known, and it doesn't get the right answer.
Complete. But within the accuracy and so on, it's known. What's not known is how the rules for making the arrows when it's protons that are moving around and so on. Okay?
When you are looking at something, do you see only light, or do you see the object?
The question.
All right, well, we'll just skip the joke. He makes a joke about food, and obviously you'll starve to death if you're not seeing your food, ha ha ha, or something. Yeah, obviously we don't see. We just represent reality. The brain just creates a version of reality. You're not really interacting with things. You're interacting with bits of energy, But anyway, bouncing off of things, and then conceptually we're making, we can imagine things that don't exist, just as they can imagine things that do exist are not exactly what they are, and so they imagine it wrong. All right, so that's probably enough. So until the next time, maybe we'll do some more Feynman, even more, maybe. I don't know. I mean, I've sort of got the point across, I think, that it's, no matter what example he gives, I can point out how it's based on this wrong assumption, this wrong description of the actual patterns. It just doesn't matter to them, the actual pattern. They have generalized it into a belief system of waves and sine waves anyway. Feynman's against waves, but he certainly is clearly articulating that somehow this notion of frequency is in this gradually on and gradually off form, and that's not the form it's in. All right, till the next time and such, so forth and whatnot. I can only reason with you people. If you're not reasonable, you're not reasonable. It's not my fault. It's clearly not my fault you're not reasonable.